All right, so we're doing a recap on Chapter 11, Quantum Theory and Light. That was Celeste. She was going to help us, but she's gone. It's good she sucks at physics. Righto, let's have a look. So the chapter starts off looking at the wave model for light. So what we're going to be looking at by the end of this chapter is this wave-particle duality of light. So it's got some wave properties and it's got some particle properties. So it starts off here, wave model for light, and it looks at this very famous experiment, Young's double slit experiment. Now, when you look in your syllabus, which I have here, it's a bit of a shine, sorry, hang on, there we go. When we look, it says, explain how Young's double slit experiment provides evidence for the wave model of light. So this is an experiment that you have to be able to explain how it supports this idea that light is a wave. Right? You also have to be able to describe light as an electromagnetic wave produced by an oscillating electric charge that produces mutually perpendicular oscillating electric fields and magnetic fields. Right, so that's that very difficult to draw model, but it's all right. Okay, so if we're going to be looking at light, it's, as I said, it's got this wave particle. No, spelled that wrong. It's got this dual. There's my Chinese. We're having Chinese for tea. Shh, don't tell anyone. Get rid of that. No one will know. Wave particle duality. So Young's double slit experiment when light goes through these two slits, they have to be very fine slits, very close together. It produces this interference pattern because the light will diffract as it goes and change its direction as it goes through each of these slits, producing like these individual wave fronts, and then those are going to interfere and produce this pattern, a diffraction pattern. That is a characteristic of waves. Waves do that, particles do not. If light was particles and it was just coming through these two narrow slits, well, you'd just expect two bright bands over here. But because it produces this very characteristic wave phenomena, we know that light travels as a wave. So we've got diffraction pattern, caused by interference. Right, so we had the slit, and as the light comes through here, we're going to have these wave fronts produced, and through here. Right. So with a single wavelength of light, a single pure colour, which is what he used, coherent light, it's the same wavelength, you get this nice clear bright and dark. With white light, you get what we saw in the Veracitum video where they had colour fringes, so they had little tiny rainbows. But again, they were very similar to this. Central bright one and then spaced apart. So that's Young's double slit experiment. Right, then you have to know, you have to be able to explain that. You have to be able to describe this. We have an oscillating electric charge, so that means it's going backwards and forwards, and it's generating this electric field, and that's generating a magnetic field, and they are at right angles to each other. They are in phase. So when this one crests, that one crests. When this one down with no amplitude, that one's down with no amplitude. Right? And they're both perpendicular to the direction that it's moving in, the direction of propagation. So this is like my cheat sheet that I'm making. Well, not cheat sheet, revision sheet. Electromagnetic radiation. And I'm going to go back and I'm going to write on here that I have to be able to explain this one, and this one is describe. That's what the syllabus wants us to be able to do. Electromagnetic radiation. So we've got an oscillating electric charge. Produces an oscillating electric field. And oscillating magnetic field. And they are perpendicular, I was going to say. To each other and to direction of propagation. So then we've got V equals F lambda. That's the wave equation. That's for all waves. This electromagnetic stuff is light. Some of it we can see, visible light. The rest of it, you can still call it light, or electromagnetic radiation is probably a better definition. But all of these travel at the same speed. So for all waves, you can use V equals F lambda. For light and all electromagnetic radiation, it all travels at the same speed, the speed of light. So C equals F lambda. So that means if the frequency increases, the wavelength must decrease because this is a constant. Right, so visible light only makes up this tiny little bit of the spectrum. Something to remember with this high frequency equals high energy. And when we get a bit further in, we'll find a formula that tells us about that. High energy. So high frequency, according to this, will be low wavelength. So if we look at the smaller wavelengths, that's this end of the spectrum is the smaller wavelengths. These are the really high energy, high frequency, high energy. So these are the ones that will do damage to us. X-rays, gamma rays, ultraviolet. Right down this other side, these are the lower energies, infrared, radio waves. Right? Those ones are lower frequency, longer, bigger wavelengths, and lower in energy. So the equations here really very straightforward. Doesn't take anything much to work out. They usually measure wavelengths in nanometers. So nanometers I've got nanometers. Nano is by 10 to the negative 9. No? Yeah, 9. 10 to the negative 9 meters. So when you've got something like 700, that becomes 7 by 10 to the negative 7. That's why it's negative 7 here. See, they weren't measuring it in nanometers. Nanos by 10 to the negative, my 9's a bit dodgy there, 10 to the negative 9. Righto. And, touch something, don't know. That's pretty much all they have now. So our wave model, it explains many phenomena such as diffraction, interference, polarization, but these other phenomena that we're about to get onto do not fit with the wave model. So that's when we start looking at the particle model. So the first one of those is black body radiation. So we've got it here. So a black body is any body that is a perfect absorber, and by any body, no, I don't mean person, I mean any object, and it will be black, that absorbs all wavelengths and will also emit all wavelengths. And what they found was that was related to temperature. So the intensity or the brightness of the radiation that it releases is dependent on the temperature, and this peak moves with temperature as well. So this line here is like a trend line for temperature. Right, so this is wavelengths. Why is that looking out of focus now? Probably because of something.